Okay, it's 8:20, so I'm going to get started. First announcements. No quiz today. Next homework, I have posted that on Wiley Plus, and I pushed it to Tuesday night. Give you one more night, one more day to work on it. It will be the starting of our practice for chapter 15, which remember the first 3 sections of chapter 15 are on the upcoming midterm. Remember the upcoming midterm is on Wednesday. So I'll do a review session Tuesday evening. 7 o'clock is what I've been doing on Zoom. Okay. And there will not be a video lecture for Monday. We're just going to use Monday's class as a kind of a review for the exam. Okay. That's everything I've got by way of announcements. So let me power up the projector. Yesterday's video lecture and class video, the Thursday class, was about conservation of mechanical energy in simple harmonic motion. Since we have a spring force doing work with this conservative force, we can apply conservation of mechanical energy, and that's a helpful tool. So we will use conservation of mechanical energy anytime we're studying an oscillating system if it's convenient. Then I talked about a different example of a simple harmonic oscillator, an angular simple harmonic oscillator. And that's an object that is suspended by some kind of a wire of some kind that you can twist. And you twist the object, thereby twisting the wire. And when you let go, the wire untwists. It exerts a torque. And it causes the object to rotate. And assuming the wire obeys the angular version of Hooke's law, you get simple harmonic motion. And so I talked about that. Today's video lecture was about the last system we're studying in chapter 15 that oscillates, the so-called pendulums. And they come in 2 general varieties in all the physics books, the simple pendulum and the physical pendulum. A simple pendulum is really an abstraction, and technically there is no such thing as the simple pendulum. Everything is a physical pendulum. But there are situations where a physical pendulum approximates a simple pendulum to a very good degree, and in that case, we'll treat it as a simple pendulum. I've got the learning objectives for this section, section 4. Okay. So for example, describe the motion of an oscillating simple pendulum. So it's just swinging in a vertical plane about some support. You measure the angle theta that the string makes to the vertical, and you watch how that angle theta changes with time. Should be able to draw a free body diagram for the pendulum bob with the pendulum at angle theta to the vertical. And I showed an animation showing the free body diagram. For small angle oscillations of a simple pendulum, and we will limit ourselves to the angle theta being small. That means theta is small compared to 1 radian. We should be able to relate the period to capital T, or the frequency F, to the pendulum's length. So that's what I've got right here. Got the standard picture of a simple pendulum. It's got a string of some length L, and all the mass is at the end in the object called the bob. There's the mass M, and the thing is swinging back and forth in a vertical plane. And we measure the angle theta that the string makes from the vertical. And the formula for the period, the time to go over and back once, period for a simple pendulum, is 2 pi square root of L over G. Depends on the length of the string and the value of little g, wherever you are, but it does not depend on M. That's the simple pendulum. Next, distinguish between a simple pendulum and a physical pendulum. My next picture draws one example of a physical pendulum. Here, you've got a pivot point somewhere up here, and the object has its mass spread out all along it. And that's different than a simple pendulum, which is assumed to have all the mass at the very end. So I've drawn this thing to look like a stick because I brought along a meter stick today. And if I could use some kind of device to support this thing, and then there would be an equilibrium, vertical, I could just displace it from equilibrium and let it swing. That's a physical pendulum, not a simple pendulum, because it's got mass distributed all along it. Okay, so you need to be able to distinguish when you've got a physical pendulum that's oscillating versus a simple pendulum that's oscillating. Okay, for small angle oscillations of a physical pendulum, relate the period capital T, or the frequency F, to the distance h between the pivot point and the center of mass. So here's my picture again of a physical pendulum. I've marked the little X where the center of mass would be. And then that up there is the pivot. And the book uses the symbol H to mean the distance from the pivot to where the center of mass is. And that's important because the formula for the period of a physical pendulum is 2 pi square root of I, that's the rotational inertia of that thing about the pivot point, over the mass of the thing times G times that distance H. So that's the formula for the period of a physical pendulum. And you've got to figure out what the rotational inertia is about the pivot point, because that depends on the shape of the thing. So you have to know what that shape is. Okay. Okay, so simple pendulums, period, physical pendulums, period. All right, next objective. For an angular oscillating system, determine the angular frequency omega from either an equation relating torque, tau, and angular displacement theta, or, this is going to probably be more common, an equation relating angular acceleration alpha and angular displacement theta. That is what your book calls, I'll underline it up here, the hallmark equation of simple harmonic motion, at least angular or rotational simple harmonic motion, and that's formula right there. And there's no mystery where that formula comes from. It's just Newton's second law, where you wrote alpha equals net torque over rotational inertia. Okay. And then you figure out the formula for the net torque, and you get a formula that has this structure. The angular acceleration equals a negative constant times the angular displacement from equilibrium. Whenever you've got an equation of that structure, you have simple harmonic motion. And whatever is sitting in this position between the negative sign and the angular displacement theta is the angular frequency squared. And that's what they mean over here by determining the angular frequency omega from that formula. You start with Newton's second law, you derive a formula relating angular acceleration to angular displacement. If you discover you get a formula of the form angular acceleration equals negative constant times angular displacement, then you know you've got simple harmonic motion. And whatever is sitting in that spot is the angular frequency squared. And I'm going to do an example later on this morning where you'll see this approach in action. Okay. You have to be careful to distinguish between a pendulum's angular frequency omega, having to do with the rate at which the cycles are completed, and d theta dt, the rate at which the angle with the vertical changes. If you know you've got this formula relating angular acceleration and angular displacement, i.e. simple harmonic motion, then you can immediately write down the formula, the result for theta as a function of time, right there. The minute you see that, you get to write this. No other proof or mathematical manipulation is necessary. Again, the minute you see that, you get to write this, because that's the solution for simple harmonic motion for the variable theta. Theta is a function of time, has some maximum value called the amplitude, theta max, cosine of what I call the blob. The blob is angular frequency times time plus the phase angle. These two constants, amplitude and phase angle, depend on what are called the initial conditions. What was happening with the pendulum at a certain time, usually t equals 0. But the omega, remember, will come from that formula right there. So there's an omega in here that's called the angular frequency. And then there's just the angle theta. And you can ask about d theta dt, the rate at which theta is changing. Given data about the angular position theta and the rate of change d theta dt at one instant, the initial conditions determine the phase constant phi and the amplitude theta max, I just said. And lastly, describe how the free fall acceleration can be measured with a simple pendulum, or a physical pendulum, in fact. All you got to do, depending upon what kind of pendulum you've made, the most likely case is a physical one, is if you know the shape of the physical pendulum such that you know I, and you can measure the distance h between your object center of mass and the pivot, then use a timer to measure the period and solve for g. And you can go about with your physical pendulum and measure the value of g wherever the pendulum is. And this alludes to a method that is used a lot in geology, where geologists, because they're interested in various rock formations, and the density of the earth where you are determines what g is where you are, they can use the value of g to learn what kind of rocks are around. So geologists are very interested in the value of little g at different places on Earth's surface. And the physical pendulum is a portable way to go around and get a measure of g. Now, there are a lot more complicated ways, but that's a way you could do it. Okay. All right, so these are the ideas we need to be able to use. So let me start using them. I'm going to do two different applications. I'm going to focus on the physical pendulum for both, whereas the simple pendulum is simple and good to start with. The physical pendulum is the more realistic one. So the first example I want to talk about is the physical pendulum with the adjustable pivot point. And so here's how it goes. We have a uniform stick of length L, maybe like this meter stick. This is roughly uniform in its mass distribution. Of course, we know the length L of this is 1 meter, but we'll just use the symbol L because the stick could be any length. And we're going to use the quantity X to denote the distance between the pivot point O and the stick's center of mass. So we have this picture. This represents the stick. We have mounted a pivot point at a certain place, O. That dot is the center of mass because it looks like it's roughly in the middle, yes? Which for a uniform stick, the center of mass should be in the middle. And so we've mounted the stick at a point O, where this symbol X denotes the distance from the pivot point O to the center of mass. And in equilibrium, the stick would just hang like that at rest. But if I displace it and let it oscillate, I have a physical pendulum with some period, capital T. But I want to imagine that I can adjust where that pivot point is, and thereby adjust X. Maybe I would mount on this stick some kind of little metal device that I could turn with a screw to fix it in place that would have a little fulcrum on it that I could mount and then let it swing. But I could change where that mount is. And you can almost see, you can see just by watching here that that changes the period. Where the pivot point is, changes the period, okay? I'm going to assume that the pivot point O can be anything from one end, doesn't matter which end the thing is symmetric, from one end all the way to the middle, anywhere from there to there. So that X could range from L over 2 to 0. Okay? All right, we're gonna want to write down a formula for the period of this thing's oscillation as a function of that distance X. It's just gonna be the physical pendulum formula right there. We're just going to tune the notation a little bit for this specific situation with a uniform stick of length L. And then we'll get a formula for the period, and then I'm going to talk about it because I'm going to get to this first question. Okay, what value of X between 0 and L over 2 makes the period smallest? And what is that minimum period? Okay, all right, so let me mute that. Now, Okay, let me get my pens here. I have what I need. So here's our first example of a physical pendulum. And the picture is, as I showed you, there's the vertical. There's the stick. I've got it. It's supposed to be a uniform stick. I'm showing it at some angle theta. There's the pivot point O. The center of mass would be in the middle. And the book, the problem, calls that distance x from the pivot point to the center of mass. So let's just start by writing down the formula for the period of this thing as it oscillates back and forth. 2 pi square root of I over mg. I'm just using this formula right here. But I'm not going to call it h like the book does there, because this problem says to call that distance from the pivot point to the center of mass, pivot point O to the center of mass, to call that distance x. They're using the symbol x here because think of x as a variable, not a constant. X can be varied. Anything from L over 2, if you put the pivot point up here, to 0, if you put the pivot point right at the center of mass. All right, now to use this formula for the period of a physical pendulum, really pretty much the first thing you got to do is figure out what's the expression for the rotational inertia of the pendulum that you've got. Okay, we've got a uniform stick like this with a pivot point somewhere up here, distance x from the center, and it's oscillating about that pivot point. So we need the rotational inertia I about that pivot point, O, not about the center of mass, unless I have the special case where O is at the center of mass, but I need to treat it now as general. O is some distance x from the center of mass. So we have to remember some physics we've already learned about finding rotational inertia when the axis of rotation is not through the center of mass. And what you want to have come to your head is the parallel axis theorem. Take the rotational inertia for an axis through the center of mass plus more. How much more? The mass of the object times the distance from the pivot point to the center of mass squared, which in this case is denoted by the symbol x, so x squared. Now this one you look up in that table in chapter 10. The rotational inertia through the center of mass of a uniform stick or rod. That's a pretty well-known formula for this. It's 1/12 m times the total length squared. So there's our expression for I. So let's substitute that in the period formula and see what we get. 2 pi square root of I, 1/12 ml squared plus mx squared, all divided by mgx. That's what I get when I apply that formula. Now notice, both terms in the numerator have an m and the denominator has an m. So those m's cancel each other out. The period of the physical pendulum, when gravity is giving you the restoring torque, does not depend on the mass of the thing, which is one of the things I mentioned in the video lecture. Now the rest of this, I'll write down what this looks like now. I'm left with L squared over 12 plus x squared over g times x. That's the gist of it right there. The period depends on, well, how long the thing is, but also mainly on the distance x from the pivot point to the center of mass. And when you think about this, there's something interesting going on, because there's x dependence inside this square root, both upstairs and downstairs, coming from different physical sources. The upstairs expression came from the rotational inertia. And that says the rotational inertia gets bigger as x gets bigger. Got more rotational inertia, it's more sluggish. It doesn't want to rotate. And that makes the period longer. But the x downstairs, where did that come from in that formula? And where did it come from here? Well, it came from there. Where did that come from? I'm going to trace it back in the derivation of this formula, but that downstairs came from the torque from gravity, acting about the center of mass. And it came from the moment arm of that torque. So what the x in the denominator is saying is that as x gets bigger, the gravitational torque is getting bigger because I'm getting a bigger moment arm. And that makes it to want to oscillate faster. So that makes the period smaller. So I've got a competition. X in the numerator from the rotational inertial, when x gets bigger, it wants to make the period bigger. But the x in the denominator from the moment arm of the torque, when x gets bigger, wants to make the period less. So there's a battle going on between one contribution wanting to make the period bigger and another contribution wanting to make the period smaller. So you get a rather interesting graph if you just plot period versus x. So I want to set this up for a plot so that we can see it. Okay, hopefully it'll show up. Yeah, I'll show it to you. But in order to make it just pretty for plotting purposes, just so we can see the plot of this thing, I'm going to show you a little trick I'm going to use to make this formula a little bit prettier for plotting purposes. So I'm going to start by factoring a square root of g out front in the denominator. Then I have next square root of L squared over 12 plus x squared over x, like that. I just brought that root g out front in the denominator. Then what I'm going to do is I'm going to factor an L squared in the numerator. I have then 1/12 plus x squared over L squared. I just factored an L squared in the numerator. And I'm going to factor an L in the denominator. That might look odd to you, but you can do it. That just means L times x over L. Then I see inside here, I've got one L downstairs and an L squared upstairs, so I can do a little bit of canceling. And then there's a square root of L just sitting there upstairs. I can bring it out front. So now I've got this out front. And what's left is, let me write it in this order, x squared over L squared plus 1/12 over x over L. That's the times there. And all I did was do a little moving around of symbols using algebra, legal algebra. This is going to be how I'm going to plot it. That expression out front should look familiar because it's on the board. 2 pi square root of L over G. That's the formula for the period of a simple pendulum of length L. So what I'm actually going to plot, as I'll show you in a minute, is I'm going to divide both sides by that formula. I have T over TS. And then over here, I have x squared over L squared plus 1/12 over x over L. So we're going to plot T over T simple versus x over L. And remember what I said is happening. We got a competition. We've got a battle going on as x gets bigger. The numerator wants the period to get bigger, but the denominator wants the period to get smaller. So what is that going to look like? Let me show you the graph. I plotted T over 2 pi square root of L over G, T simple, versus x over L. This is what a physicist calls dimensionless axes. Both quantities on both axes have no units. And x over L ranges from 0 to a half, because x can range from 0 to L over 2. And there's the plot of the function I just wrote on the board. And the point is the competition between wanting to make the period get larger and the period get smaller means, although it's pretty broad, there's a minimum of the period. There's a value of x over L somewhere roughly in here where the period is smallest. If that's your goal, if your desire is to have the smallest possible period of the oscillating stick, then you would want to find where that is. What is the x over L value? But first, I just wanted you to see that there is a minimum in the period. And the x over L where that is somewhere between 0.2 and 0.3. Our job in part A of this example is to calculate exactly where that minimum is. Okay, that's what we're going to do. So let me get my working space back. And let me show you how we're going to do that. I've explained most of the physics now and why we're going to get a minimum, because we've got a competition between x values in the numerator and the denominator. So now it just boils down in part A to finding out what value of x, or x over L, gives me a minimum period. And I could use this form, but I wrote it this way mainly for plotting purposes. The form I'm going to use for doing this next calculation is this form right here. So let me start by writing that. 2 pi over root g square root of, I'll write it like this, x squared plus L squared over 12 over x. Okay, again, what are we doing? We're finding the value of x where the period is a minimum. Your Math 110 professor would want you to know what that's alluding to. If I give you a function of x and I want to find the value of x where that function is a minimum, we know how to do that, right? We take the derivative of the function, in this case the period, with respect to x, set it equal to 0, and then solve for x. Well, okay, so we're going to have to be able to do that. Let me get myself some space here so that I can do it. This is good practice with our calculus too. Now to help me do that derivative, let me write the period formula one more time. Well, actually, I'll write it a couple of steps so that I won't go too fast. I'm going to break up the numerator and denominator into their own square roots. There's the numerator. There's the denominator. You can do that. Next, let me write it like this. This next one might look weird to you, but this is the way I find it useful to do the derivative. This up here, I'm going to write like this. Right? Square root means 1/2 power. And that's a square root of x, but it's downstairs. So I'm going to bring that x upstairs, so times, but the x will then be to the minus 1/2 power. Square root of x downstairs means x to the minus 1/2 power upstairs. And now I'm going to start the business of taking the derivative of that with respect to x. And I wrote it this way so that I can see that I'm going to have to use the product rule. Okay? I don't use the quotient rule. The quotient rule is the product rule. Right? It's not a new rule. It's just the product rule. Okay? I have long ago forgotten the quotient rule. I don't need it. I just need the product rule because I have a product. So here we go. Doing the derivative. This is just stuff independent of x, constant, multiplying out front. So that just gets carried along. Product rule says take the derivative of the first function times the second, plus the first function times the derivative of the second. So that's what we're going to do. This is the first function. This is the second. Let me put some brackets here. And yes, I'll have to use the chain rule as well. So there's the first function, x squared plus L squared over 12, all to the 1/2. So the chain rule gives me 1/2 x squared plus L squared over 12 to the 1/2 minus 1, which is minus 1/2, times, chain rule, the derivative of that blob with respect to x, 2x, times the second function, x to the minus 1/2. That's the derivative of the first times the second. Now, plus the first function, x squared plus L squared over 12 all to the 1/2 times the derivative of the second. That's just going to be minus 1/2 x to the minus 1/2 minus 1 minus 3/2. Close square bracket. I'm going to require that to equal 0. That looks pretty intimidating. But let's not let that stuff intimidate us. Let's be methodical and see how we can write this to simplify things, maybe in a way that makes it easier to see what to do. Just look for ways to simplify this. You got a 2 upstairs and a 1/2 there, so those 2's cancel. In this first term, I've got an x upstairs, and then these negative exponents mean they're really downstairs. I've got a square root of x and a square root of x squared plus L squared over 12. That's, I think, what I've got for that first term. Next, whoops, there's a minus, careful of that. Minus 1/2 square root of x squared plus L squared over 12 over x to the 3/2. That's convenient to put things back downstairs again if they have negative exponents. What the heck do we do with that? Well, keep going. Let's have some calculus courage. Let's factor things that are common out front. Okay? Doesn't look like there's much, but there is a little bit. Downstairs, I have at least a factor of x to the 1/2, 1 over square root of x. And if I do that, I'm left with, in the first term, x over square root of x squared plus L squared over 12 minus 1/2 square root of x squared plus L squared over 12. And I took out an x to the 1/2. That leaves me with an x to the 2/2, which I believe is x. That must equal 0. All right, keep going. What to do next? Well, I looked at this stuff inside the square bracket. Still looks a bit intimidating. But I said, well, it's one messy fraction minus another messy fraction. And when you subtract fractions, you're supposed to get a common denominator. And if you don't know what else to do, you can always take as your common denominator the product of the 2 denominators. So that's what I'm going to do. I'm going to get a common denominator of x times the square root of x squared plus L squared over 12. That's my common denominator. So that I can then subtract these 2 numerators. Now we got to be careful. With this first term, to get the common denominator, I have to multiply upstairs and downstairs by an x, but I already have an x, so that becomes an x squared. So I have to multiply by x up and down to get that common denominator term there. Minus, what do I have to do to this term to get the common denominator? I have to multiply up and down by the whole square root of x squared plus L squared over 12. So I got a 1/2. And that becomes x squared plus L squared over 12. Close square bracket must equal 0. Okay, let's keep going. Calculus courage. I want all that to equal 0. What the heck do I do with it? Well, if I have a fraction and I want that fraction to equal 0, the most straightforward thing is to have the numerator equal 0, as long as the denominator doesn't also equals 0. So I'm just going to force this blob in the numerator to equal 0. Then that will make this whole thing equal 0. Remember, I'm requiring the derivative to vanish. So all I really have to do is take that numerator inside the brackets. X squared minus 1/2 x squared plus L squared over 12, that must equal 0. That was a big step forward, observing that that's what has to happen. So now let's just finish that math off. Take that one term over, x squared equals 1/2 times x squared plus L squared over 12. Multiply both sides by 2. 2x squared equals x squared plus L squared over 12. Take that over. X squared equals L squared over 12. X equals L over the square root of 12. Or, another way to write it, X over L equals 1 over the square root of 12. If you want a decimal approximation to that, to 3 sig figs, it's 0.289. So when X over L is 1 over root 12, that's when the period is a minimum. Let's check that on our graph. Because we've got X over L along the horizontal axis. 0.289 is right about there. And you go up, and this is very broad, but that looks like that could roughly be the lowest point. Okay. For this meter stick, we can mimic that to some extent. First of all, notice if the X over L, if you go all the way down to 0, that amounts to putting the pivot point right at the center of mass. Guess what? You don't get any oscillation. They put it like that and it stays that way. No period at all, or the period is infinity, because it never oscillates. That's what that says, going up that way. But I can put my fingers, the pivot, at a number of different places. All right, but the minimum period should be when I'm just about 0.3 for X over, that's just about 30 centimeters from the middle. Let's start up here. Let's start near the middle. That should be a pretty big period. Of course, there's friction with my fingers. Okay, but that's a pretty big period. Should be a a little bit longer period if I put it up here compared to the minimum. But if I put it about almost 30 centimeters from the middle, that's the smallest period. Okay, and we just found it. It's when X over L equals 0.289. Then all it asks for in part B, the hard work's over, folks, thank goodness, is to actually get the minimum value of the period. That means just go to the period formula and substitute X equals L over the square root of 12. All right, it's just math, so I'm going to write down what you get. You see if you can get it. The minimum period is 2 pi square root of L over G, that's out front, times square root of 12 over 6. If you divide that, remember that's just what I called T simple, the period of a simple pendulum. That's this. You have just this part. Square root of, it's rather interesting looking, square root of 12 over 6. Decimal approximation to that is 0.766 to 3 sig figs. And that would be on this axis then, at the minimum. So it's roughly about there. And then you go over there. Yep, you're just a little bit less than 0.8. Okay, 0.766. That's a physical pendulum. There's actually quite a bit of interesting stuff going on there. Okay. All right. Now I want to show you one more physical pendulum, but I want to change it up just a tad. This is a physical pendulum, wherever the pivot is, where the restoring torque that's trying to get it to equilibrium comes from gravity. But you can have other scenarios where the restoring torque isn't coming from gravity. Let me show you. Okay? Goes like this. We're going to get a restoring force from a spring in this case. Here we're looking in an overhead view of a long uniform rod like this, of a given mass that's free to rotate in a horizontal plane about a vertical axis through its center. So I want to be clear, like that. Like that, not like this. Horizontal plane about a vertical axis through its center. This is how it's oscillating in a horizontal plane. Let me get that so that it's exactly horizontal. Back and forth, then back and forth, then back and forth, like this. How are we contriving it to go back and forth? We're connecting a spring to one end, and the other end of the spring is just connected to a wall. And the spring has a spring constant that's given, little k, connected horizontally between one end of the rod and a fixed wall. When the rod's in equilibrium, it's parallel to the wall. What is the period of small oscillations that results when the rod is rotated slightly, like this, and released? So let me draw my own picture, and I'll show you how we tackle this. So this is a physical pendulum, but the restoring force is coming from a spring, not from gravity. So it's a physical pendulum. Restoring, I'll call it a restoring torque from a spring. So we have the overhead view. We're looking top down. First, I'll draw the equilibrium picture. You've got this uniform stick of length L with a uniform mass distribution. So the center of mass would be, of course, right at its center. And then here is the wall. And at one end, the stick is connected via a spring to the wall. And in that configuration, just like that, the spring is neither stretched nor compressed. No spring force, no spring torque, the thing would just stay like that. But then what we're going to do is rotate it about the center of mass a little bit. Now I'm actually going to draw more than a little bit. There's the equilibrium configuration. I'm exaggerating this picture so that we can see a little better. That's a pretty big amount of rotation, but that's okay. Notice then, again, you're looking down from above. By rotating a little bit about the center of mass pivot point, that's the pivot point right there, we're stretching that spring now. Okay, we got a spring that's stretched. So we're getting a spring force. That would be right along the spring itself. Right? We get a spring force. And that spring force is going to give us a torque about that pivot point. And that torque is going to try to restore the rod to equilibrium. So we have a restoring torque. So we have a chance to have simple harmonic motion. How are we going to show if we have it? We apply Newton's second law, rotational version. Angular acceleration equals net torque over rotational inertia. Or if you want, you can write rotational inertia times angular acceleration equals net torque. Same thing. But the rotational inertia and the net torque must be about the given pivot point, right there in the middle. So let's figure out what to put for those things. Let's focus on the torque for the moment. The torque is coming from the spring force. The formula for calculating torque, at least this is one way to do it, is take the magnitude of the force that's giving you that torque times the distance called the moment arm. I like that approach when the picture is relatively simple. Magnitude of the force that's giving you the torque, in this case F spring, times what's called the moment arm, which we're going to have to identify. But we better get the direction as well. Remember, clockwise torques are negative, counterclockwise torques are positive. There's the pivot, there's the force. It's wanting the stick to rotate clockwise, so it's a negative torque. And over here I have I alpha. Now, here's why I drew an exaggerated version of the picture down here, because I need to be able to see that I have a right triangle with two sides there and a third side there. And we're going to call this angle right here the theta that's important. That's the angle that the stick makes with the dotted line, which would be equilibrium position. Then, note, this length along here on the right triangle is the hypotenuse. It's just L over 2. The length in red, that's the moment arm, R perp. Perpendicular distance from the axis of rotation to the line of action of the force. So now I'm going to write down expressions for those two things on the right side. Minus moment arm, that length right there, the red side of the triangle. But I've got a right triangle with a hypotenuse L over 2 and an angle theta. So L perp from trig is L over 2 cosine theta. Now, what about the spring force magnitude? Well, that's the spring constant K times the amount of stretch in the spring, Hooke's law. Well, how much stretch is there? It's that distance right there, which is the other side, the other short side of the right triangle. So that's L over 2 sine theta. And that must equal I alpha. The I, by the way, is ML squared over 12. Where'd I get that? Look up that table in chapter 10, rotational inertia for a uniform rod with the axis through the center. ML squared over 12. Now, what am I going to do with that? Because that looks bad. Remember the hallmark equation for simple harmonic motion? For rotational version anyways? That's how I know I have simple harmonic motion if I get an equation like that. Angular acceleration equals a negative constant times angular displacement from equilibrium. That's that theta right there. There's an alpha, but that's a lot more messy than just theta. There's a cosine theta and a sine theta. If you just try to solve that, you're done for. You can't do it. But you use what's called small angle approximation. Theta is much, much less than 1 radian. And I mentioned that already on the lecture video, at least as far as sine theta is concerned. When theta is very small, the first term in the so-called Taylor series for sine theta is just theta, with theta in radians. So we're going to replace sine theta with just theta. Since if the angle is small, that's a good approximation. But then what do I do with the cosine theta? What's the approximate version for that when the theta is small? Well, for that, you need what's called the Taylor series for cosine. And the first term in that is just a 1. Remember, cosine theta when theta is 0 is exactly 1. So I'm going to replace cosine theta with 1 and sine theta with theta. And then I have ML squared over 12 times alpha equals negative, what's left? K L squared over 4 times theta. Let's see if things simplify. Oh, look, the L squareds on both sides cancel. And I can do some canceling here and leave me with a 3. And then I can solve for alpha. Multiply both sides by 3 over m. I have negative 3k over m. Have I dropped anything? All times theta. Make sure I haven't dropped anything. K, I had an L squared and I had a 4, that became a 3. I don't think I dropped anything. Okay. Now compare that with the Hallmark equation for simple harmonic motion. It's exactly got that structure. Alpha equals a negative constant times a displacement from equilibrium. At that point, you can just state simple harmonic motion. And you know what the angular frequency squared is. It's what's sitting right there between the negative sign and the theta. So the angular frequency squared is 3k over m. Okay. Oh, let's see. Make sure I have it. Good. So omega is the square root of 3k over m. And what I want's the period. So remember, next step, just come down here. Period is 2 pi over angular frequency. And now use the formula for the angular frequency, but it's downstairs. So you get a square root of m over 3k. And now you have the formula for the period. Depends on the mass of the stick and the spring constant, but not how long it is. And we're given the mass and we're given the spring constant. And so when I plugged in those numbers, I got 0.0653 seconds, 65.3 milliseconds. It was a very stiff spring because I had a very big spring constant. Okay, so that's our discussion of pendulums. Class on Monday will be a kind of a review. Talk about some of the key things we've been talking about for the upcoming midterm and give you a chance to ask me questions. Okay, so no video lecture for Monday. Okay, that's all. Good weekend.